Like you've only made a mistake. I would go.
The mentee problems.
Well, I love it.
Oh, you probably do.
All right, let's do another example. So I could take any subset. Let's take y equals z, which, you know, it's really difficult to work with topologies on z. You think it's easier, but it's actually harder. And with x equals r, usual topology.
Give you. I handed in my favor. I was trying to make sure.
Yeah, I think he did. Yeah, I saw some stuff downstairs. All right, just at your desk, play around with this one and see what the open sets are going to be in this topology, in this subspace topology.
Just write it down, picture it looks.
No, just think this one through. When you think you've got it, just let me know by looking at me, I guess. I think you got it. What are you thinking, Lauren?
Why is the integers and x is your real numbers in usual topology? If I'm thinking of it right, it's the null set and x.
Could you get anything else when you intersect an open interval with?
Just
Can you get a singleton?
yeah, that's what I was thinking.
Can I get anything more than just a singleton point? What do you think, Sebastian?
Make a larger.
Subsets of integers?
Yeah.
Do you think you get all subsets of integers?
Yes.
Really? Can you get the odds? Only the odds as a subset? Sure about that?
Well, because. Oh, yeah, you could. You could.
Why do you get only the odds?
You wrap each odd number in some small interval that doesn't include.
And the reals.
In the reals, so like from 0.5 to 1.5.
So here's where it's not effective to think about the basis. It's just one open interval, right? Right, because if you can put a surround each odd and then union those, right? So what can I get? I can get singletons. can just use something like that, 0 to 4, and then so I'll get 3 of them. You know, I can make as many of them as I want. So how do I get the odds? I can just do this. So yeah, do this right. I'll just show you how to get one odd because I don't know if I can symbolically do this right now. So let's say I want to get the odd 1. So to get the odd 1, I'll just do 0 to 2. This is number, not odd equals. So I just do that for each odd number, I'll get one open interval that doesn't have anything in the intersection but that odd number, and then just union up those open intervals, they're open, and then boom, I've got all the odds. Anything else you think won't be captured in there? Did we do discrete topology on C?
That's not.
I don't think we have any topologies that we talked about. It's the power set topology on Z. Discrete topology, we usually use empty set X, and discrete topology, he might have, if he's talking about metric spaces, is that the distance between any two sets is 1, unless they're the same set. That's usually what we talk about as discrete topology.
Like we've done it as any subsets. Yeah, right, like that's what Dr. Adams. Like,
Yeah, maybe. Yeah, I don't know if Dr. Doss was using the book for it, but typically when we talk about metric spaces and discrete topology, we just allow the distance between any 2 points that are not equal to be 1, and then the distance between points that are equal to be 0. I'm not sure what terminology he used. Trying to think if he would have a metric upon what Dr. Adams calls the discrete topology. I'll ask him. All right. So one of the things about, okay, let me give you 2 facts. Oh, let me ask you what the closed sets in this is a topology in its own right. What do you think the closed sets would look like? It's everything, yeah. So power sets, yeah. We've done this before in general. Yep, it'd be all the power sets. You can have closed sets. And they're exactly what you think they would be. The closed sets in Y are going to be complements of open sets in Y. I'm going to back up on the topology we just created by inducing underneath this subspace topology. Again, what Tim had talked about, we've got things in that Y that are open that weren't open in the original topology. So you get like new things. And in that way, these subspace topologies are very different than subspaces in the vector space world. And also when you do, oh, maybe not in quotient groups. I think in quotient groups, you'll get something. You can get things that are weird and different. But it's like wrapping your head around that. So 2 facts. I'm actually going to give you relief from homework this week, but this would be a good homework problem. I was looking at it and going, this is a good homework problem. Let's see. So I was actually thinking that you might say the following for closed sets. I'm not sure if this is hard, but it seems like it would be straightforward to show that this closed sets in Y are gonna be complements of open sets in Y is the same thing as this. These two things are the same. So, I might have gone to this. We define the open sets this way. Maybe we could define the closed sets, and they turn out to be one and the same. And the second thing that's a fact is you were already using it. And I saw some, I think, yep. So John had it on the board. For X, a topological space, and B, a basis of X, if Y is an X, then the basis for Y is really the basis for X. Intersected with Y. And you were kind of using that when you were doing the first one I gave you. You were taking just the basis elements and intersecting them and seeing what you get. You know, that's why I like text. Because you have to actually really think about what you think because you're using your thumbs. It's not what you would think. I had mentioned it to MA 103 that I just give my number so that if they have a question while they're doing their homework, they can text me and they're like, that's not a good idea. And I'm like, why not? Because when you're texting, you sometimes answer your own question because you really have to think hard about what you type. And that's not like an email where you can put a stream of consciousness. You have to use your thumbs and type something out.
Well, to be seen every thought I had.
Yeah.
And you can't just say, I don't get it on a text. That's really hard to do.
Yeah, you have to say.
I've never got one that said, I don't get it. I usually get like, but someone can definitely come to AI as a plebe and say, I don't get anything. Teach me again. Question, Lauren?
Ma'am, so for the second X, BY, is that a basis element of Y?
So yeah, this is the basis for Y. So
That's-
BY, so like, yeah, that's a good point. I should define that.
The Army game. You know how when they do the prisoner exchange, they like people like have things on their back like duct tape or whatever.
Oh.
The like West players on exchange at the day with me, they like went in out of order and it was being KB.
That's the type of thing we, like, our group this year, like, I'm so scared we're gonna screw this whole thing.
Supreme correct.
We all want to go.
It's gonna be hard for you to be here during Army Navy week. We had a Navy guy in the department when I was young here, and we toilet papered his office. We did all kinds of stuff to this poor guy.
Like, you guys have fun, but they can't.
All right, so topologists need to be able to draw good pictures. I'm way too messy to draw good pictures. I'm going to try to do this. So when I write C, and Colin Adams talks about this in the book, C is not the topology, it's actually this unit circle. And I'm just going to draw this out to show you what this is because we're going to come back to it. Yeah, so you're in R3, so you have the three axes, and you're going to consider a two-dimensional circle inside R3 in the XZ plane. So I'm gonna take that circle. And it's on the XZ plane. I'm gonna rotate it around the Z axis. And when I do that, what do I get? Physicists. If I take a circle and rotate it around the Z axis, which is, you're not this way, you're this way. You're a math class.
It's just solid loss.
Think of it as like
Wait, what?
a unit circle, so it's away,
Sort of centered on.
not centered on the origin. Get a torus. So I'm gonna do my attempt of drawing this out. You guys are supposed to be better.
DOS defined it as. Yeah. As reviewed like one.
So S1 has the topology. We're not gonna have the topology on it. I'm just gonna take a circle, a unit circle on the XZ axes. I'm thinking he's taken,
So it's a. Has ever like that totally.
okay, this is my version of a torus. Deal with it. It's topologically equivalent to actually being a torus. So you get kind of a donut.
It's done the same thing, it doesn't. That's funny though.
Which tells you how nerdy you are if you think that's funny. So this thing, we're gonna come back to this. So he just introduces it in this chapter, but he's gonna come back to this torus. We're gonna equip it with the topology and use the torus. The torus is used so much in topology, and algebraic topology is used quite a bit. In fact, I just messaged my algebraic topologist friend, like, I was thinking of you when I was trying to draw these things out, because they'll always have these shapes drawn out and they'd be studying dynamics on the torus, or dynamics on pair of pants was one of his favorite. You'd have a pair of pants, 2 holes, like they do topology on top of that. Yeah, he had a hard time finding a job. He had a very hard time finding a job.
Yeah, I think actually.
One more drawing.
A pair of pants technically has 2 holes. It's fully connected. That's the question. 1 minus the number. Or in number of. Yeah, that was like an arbitrary definition.
Yeah. Yeah, you should source the because so, yeah, it's just a human.
Assume that isn't correct. Consider that. Like, so that means your mouth. And that's just 2 holes.
No, that'd be.
Yeah, exactly. That's
According
Let my hypothesis if the number of holes minus 1. Or,
Yeah.
yes, but if your mouth and nose are
to-
connected, then it's 2 holes. It still doesn't make sense.
Actually, yeah, that.
Look at this.
But how many holes in the straw have?
Hey, one water bottle is a torus.
The cylinder.
But if you consider just our.
Oh,
That's.
the donut and the coffee mug. All right, another one. This is you just can take a surface in R3 and then punch holes into that surface using, like, take a ball and punch a hole through it. So you get these patches if you punch holes through it. Those patches end up being a topology. So that's an intersection, right?
I love this.
Is the topology of the rootless right now?
So there's these famous problems in partial differential equations where you have, I think it's called the Stefan equation, where you have a ball of ice and you want to drop it into something and the ball of ice is melting and you're trying to describe that with a PDE. Sometimes we change the topology to work on these smaller topologies because the math gets a lot easier. So they do have applications. He has them in the book. I didn't really notice him doing PDEs, and maybe that's a bit of a stretch for him. But I do remember seeing these types of equations when I was doing PDEs. Do you guys talk about those kind of equations where you have something that's melting in another medium? It's probably a lot, it's probably really hard to do that.
Not built. Engineering. Applied physicists.
Okay, I'm going to now go to quotient topologies. And I'm probably not going to finish all the way, but I'm going to try to get through some of them. So in the closest analogy is an abstract algebra where you have quotient groups. And the idea of quotient groups, why we call them quotient groups, and did you guys use Fraley as your book? Fraley has some really good pictures of what a quotient topology is. It's a quotient, you're dividing. So when you take 6 divided by 3, you get 2. You collapse, you're really taking 3 and boxing them into 2 pieces. That's what you're doing when you quotient out something. So he has these nice pictures of quotient groups where you have the big group, which is bigger, and then he blots out the quotient group and you see smaller groups inside the bigger group. So it's kind of the same idea. You're starting out with your big topology and then squishing down and reducing it, but you do so with a function. So actually, I have a picture to show you. This is how we're going to get the Mobius strip and all those kind of things. I didn't even try to draw this. I actually did try to draw this, but here, this is an example of a quotient topology where you start out with a plane. So you can actually take a piece of paper, wrap it around and glue it so that you get a picture like this. And then you can twist that. I was doing this in the plane and everybody's like, how is she doing? So I was trying to, like, you take the ends around, attach together, and you can get a torus. So you can get one topology to give you and induce another topology. So the plane will turn it into something like this. If you take a planar region.
Doctor, I'm gonna ask another question there. Mathematically, how would you?
We're getting there.
Okay.
So I'm gonna put some rules on this.
Precursor.
Yeah, so you get a cylinder
You get a cylinder.
and right.
Cylinders equivalent.
Yep.
You have to define that like square to start with, it's like a modular space in that like it's. Otherwise.
I can do just like I did 0, 1. I could do 0, 1 cross 0, 1 and get just a square, and then I can do this.
It's like making pizza. Tim goes to ours being something. Yeah, basically making pizza.
There you go, Sebastian. There's your definition. I think I usually do this.
That's what I always do think about. I just think it was more like
I just like the way he like, stop like definition.
everything paused.
All right. Yeah. No, I'm like more stream of consciousness type of person.
Topological pizza is. Topological pizza is said to contain pepperoni.
Absolutely not.
For a physicist, it contains pineapple.
So suppose I have a topological space and I have another set. It doesn't necessarily have to be in the original set.
Yeah, there's some topologies you should cross.
Yeah, I feel like
You just go both wine and do ham and pineapple. I have a pepperoni pizza.
He took your receipt.
I know,
And if you're eating it New Jersey style, you're doing it topologically. You're folding it.
But
Oh, it's some top one.
I'm not necessarily trying pineapple on pizza, but I think the only time pineapple belongs on pizza is when it's part of Hawaiian.
You know, I put these all on YouTube. Merle Scaletti goes through our class.
They use the videos on YouTube.
Guys, it really helps me out with
sandwich. Disgusting.
Usually it's a p. So not to be confused with p-value. It's this is a function that takes the topological space X and then maps it to A. And let's suppose I have a subset. I take it everybody's hungry in here.
Salad sandwich.
Dude, the carbohydrate theory of sandwiches
What is that?
is the most comprehensive theory of classifying foods as types of sandwiches.
What is it?
So basically, it depends, like, if you think about a cube, and you can generalize any food item as a cube, and then whichever faces have bread is how you can conceptualize that thing. So like, take.
All right.
Let's put a pin in that.
We're gonna table that one. Back.
You can come on my steering committee meetings and discuss it.
They got a great.
It'd be great because I don't think they'd ever talk to me again, which would solve a lot of my problems.
Fellas, check
It's
this
not
out.
that in San Francisco.
Calzones.
All right, so you start out with a big space. I'm not sure how you guys define quotient groups in abstract algebra. Use a map. You didn't use a map? Okay, so we're using a map to do our quotient topologies. Start out with a big space and any set, it doesn't necessarily have to be inside X. I have a surjective map so that it's into my A. And I have a subset U, it's going to be open in A if the inverse map is open in X. That's how you define your open sets.
Okay. Man, so when like this thing in topology is the defined subset U.
Go in there. I'm not done with this, like a 2-slide definition. So far, are you with me? I think they would understand just carbohydrate and hot dog. They wouldn't understand anything else. Okay, ready?
Yeah.
All right, second slide.
Well, the end conclusion of that hot dog house.
So the resulting collection of sets
I gotta go down, which is saying the most vital stuff.
That would be good.
So this is the quotient map. Topological space. Yes. I'll change colors when we stop this definition. So modular arithmetic is an example of this. I know that you study that in abstract algebra. If you had a foundations class like mine, we actually do it because we do a little bit of number theory, which is my favorite area of mathematics. So you really rethink what quotient means. You know, this is how I taught my kids how to divide, actually. I would take these singleton cubes and have them group them in smaller packets. That's really what you're doing when you divide something. So I mentioned 6 divided by 3 is 2. You're really taking them 6 cubes and then putting it into packets of size 3, and I have 2 packets. So that's a similar idea here. I have something big, possibly, and then I maybe have something smaller, possibly, because X and A could be anything. And then I have a way to take that big thing and reduce it down to the small thing by using a concept like division. So this is kind of like division, right? You can even define maps to define division.
This might be a weird question.
So we have also embeddings that's coming up. Okay. I'm gonna prove this is indeed a topology and we'll close there. I wanted to get to all the Klein bottles and Mobius strips and everything, but it's gonna probably be, I'm hoping it'll be in our next class. It might not be. I still have, I'm only halfway through my notes. So
Yeah. Eigenvalue. We can figure out. It didn't have, measured and gave.
that
That's,
Yeah.
that's when he starts this house, like working on the math of time travel. It's like, like a Mobius strip. To keep eigenvalue.
you just said a whole bunch of stuff that doesn't go together.
Yeah.
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 Like things that people think when they hear math major, and it's either that or it's you're just multiplying really big numbers.
Take eigenvalues of really big numbers. Mobius.
All right, first one's easy. Get the easy stuff knocked out first. The inverse of empty set is empty set, which is open in X. And P inverse of A is X because I did say I would change colors. P is surjective. It's onto. Both of these guys are open.
So quotient topology isn't just like one topology, it's a family of topologies induced by some P dividing function.
You need that function. It's just one topology. And I'm actually going to show you some of the topologies we've worked with can be induced from something that you also know very well. I'm going to show you that in a second. The second criteria, these criteria are all easy. I actually gave these problems, not with uncountable unions, but let's suppose I have a collection of sets. I'm going to put my tail on this. Beta, this is my beta. Draw that better. So put a tail on it. There's my beta. Be open in A or beta belonging to an index set. So it could be uncountable. Remember, that was a big deal. And then I stick this union inside here. And this is Foundation's first few homeworks. I didn't give him something uncountable. I gave him countable. Foundation's homework. Yeah, B is an index set. So let me swap colors here. If you want to put an extra note, it doesn't have to be countable. So I love how I gave these in Foundations. I would ask them first, is it true? And they've really gotten good at kicking the tires with examples. And, you know, I gave them a whole bunch of problems where I didn't even know if they were true or not. So they come and ask me, is it true, ma'am? Is it true? I'm like, I don't know. Figure it out. And so I think one of them said last time, like, I was hoping this wouldn't be true, then I wouldn't have to prove it. Took it further than that, though. I said, if it's not true, what restrictions would you need on those functions to make it true? Yeah, I'm gonna give you some for your final.
You ever say prove this, like not like is this true, but prove this.
You think I'd be that mean?
I don't know, man.
Yeah.
Well, I hope so, man, because that is what I said for the tool. That's what it is. In this case, I
He's like, in this case, I'm here.
Okay, the third one's just as easy. It's foundations homework again, part 3. I didn't close out part 2. Part 2 is done because since P inverse of each one of these U betas is open and X was a topology. Not yet. I just erased it so I can close this out. So that P inverse of U beta is supposed to be open. Third one's also, the third property is countable. And so third property comes out as well. So suppose I have a countable set of open sets. Just to remind you, you're going back to the other set all the time to because the definition of open in A is dependent on going backwards to the other set that you know is a topological space and proving that that's going to be open. So this is going to work out the same way. I think they're countable, but I could be wrong.
can't either.
Yeah, it might be finite. You might be right. I forgot the definition of topology. And this move right here, you should have done something like this in a foundations class. Proving if you have a function that you can pull things in and out. All right, I'm going to stop there because I'm going to show you some examples next time and then make you think of like weird examples where you actually have something that smaller. This is usually used with something smaller. You break things up into packets and then work on those packets. Z to Z2 is my favorite example. Z, take the evens, put them in one box called 0 and put the odds in another box called 1. And I've taken the integers and packed them up into 2 boxes. So that's usually how we use quotient topologies. Coming next. All right, any questions?
Yeah, same. Good. ones, but it's just like.
Like, you know, the.
Yeah.
Yeah.
I just wanna make sure I didn't terminology. Okay. So you got it, I think. The.
A is the quotient topology,
Folks on.
and the map is the quotient map. Yeah.
And then you have a set that you're kind of going.
So that's the hard part, the U, you have to go back to the, no, the U is actually in A, but you have to go backwards to show that it's actually open.
Oh.
Thanks.
Yeah, so you use subset of A, but then you have to show that. in-
Yes, when we work examples, I have some laid out for you guys to just pull around on the board, you'll get the feel for it. Like, you're in this other planet and you need to go back to the original planet to see if it's open and then come back this way.
So like we make those transformations, you have to go in the diagrams. If you wanted to prove something in one, you have to go back to the resume, say that it is.
Actually, yeah,
Okay,
yeah.
makes sense, but like, I feel like that would be very.
But so the goal is if you have a quotient topology, you want to characterize what those open sets look like in that quotient topology itself. Kind of like what we were doing on the board with these, you know, when you have a subspace, same thing. You kind of want to know exactly what the open sets look like, you know, rather than having to go back and forth. Yeah.